This video is going to look at the fundamentals of factoring quadratic polynomials. To start out, we're going to look at the features that are needed in order to factor, and then we'll look at kind of a thought process that you can go through if you're trying to factor a quadratic polynomial. You have to remember that quadratics don't always factor, so this won't always work. But when it does work, it allows you to break something down and possibly find the roots or the solutions of a quadratic equation. Okay, so to begin with, I'd like to start with a simplified situation. So I'd like to start with a quadratic that has this structure. X squared plus, I'm going to use p as a coefficient of x and a q as the constant term. And right now, we're going to say, or think about, p and q as being known constants. But we're not going to specify anything more about them. So they could be positive or negative, any combination of the two. So this is the kind of standard canonical form of a quadratic with a coefficient of 1. And what I'd like to do is I'd like to match this up or try to connect this to a factored quadratic and see what the connection is between the coefficients that we see and the numbers that eventually appear in the factored form. So what I'm going to do is I'm going to impose equality between this and a factored form of the same polynomial. So I'm going to say that if this is going to factor successfully, it's going to factor into two pieces. And those pieces might have different, be different factors. They might have different roots. So this will be our starting point. We'll be looking at this, and we want to know what is needed in order for this to be equal to a factored version, which has the structure, say, x plus a times x plus b. So the p and the q are the coefficients in the canonical form of this quadratic, and the a and the b, those are going to be the factors. Or those are going to be the negatives of the roots of the polynomial. Okay, so these features are the numbers that appear in the factors. Okay, so if we're going to be able to move from one of these representations to the other, back and forth, factoring goes this way, foiling or multiplying out goes this way, then let's just put them in the same form by using polynomial multiplication and then match up the different features. And that'll tell us what's required in order for this equality to hold, in order for these two things to be the same. It'll give us a link between the coefficients of the standard form of this quadratic and the numbers that are appearing in the factors of that same quadratic. Okay, so we're going to multiply this out. So x times a times x times b will distribute the first polynomial across each term in the second polynomial. Okay. And then we'll distribute the x across and the b across and combine like terms. Okay, so when we do that, we get an x squared term, an ax term, a bx term, and an ab. So if I combine like terms, I get a plus bx plus ab. Okay. Now, if these two things are equal to one another, that tells us the different parts that have to match up. We've looked at a special case where the x squared has a coefficient of 1, and that matches perfectly. Okay. The requirements that we need to fulfill when we're factoring are that the other two pieces match up perfectly. So what we need is two numbers a and b that are chosen in such a way that the coefficients in the quadratic that we're trying to factor match up with them. So we need a plus b to be equal to p. That's going to be a number that we know when we're factoring. And we need a times b to be equal to q. Those are the two requirements that are needed for this polynomial to be equal to the factored form. Okay? So we need a plus b, the sum of those two numbers, to be equal to p. This is the coefficient of x in the polynomial that we're starting with, and we need their product, a times b, to be equal to q. And this is the constant term. In the quadratic. Okay, so those are the different pieces that we need in order for this process to work. All right. So let's explore some examples. By thinking about it in this way, we're not breaking down factoring into lots and lots of different cases. We're thinking about the problem more holistically. I find that this is a little bit more natural because I'm not worried about a lot of different things. I'm just trying to make these two properties hold. So I think it simplifies the presentation all in all. Before we do any actual factoring, what I want to do now is I want to show you that these conditions are perfect. They do exactly what we need to make sure that this equality is true. So we're going to start out by not factoring, but by multiplying out and making sure that we start to see the pattern where the numbers and the factors give rise to the p and the q. Okay? All right, so let's do a couple of different examples. Suppose we have x plus 1 multiplied by x plus 3. Okay? If I multiply this out, I'm going to use the distributive property twice and then combine like terms. And what I should find is that the a and the b that are in these factors should match up to create the coefficients p and q in the standard form of this polynomial. So let's just kind of use the pattern that we just worked with to predict what this is going to be without writing it out in terms of a bunch of different steps. So what we should see is an x squared term. Right? And then the coefficient of the x term in this quadratic polynomial should be a plus b. It should be the sum of these two numbers. So 3 plus 1 is 4. And then the q, the constant term, should be equal to the product of these two numbers. 1 plus 3 is equal, or excuse me, 1 times 3 is equal to 3. So when we multiply this out, this should be the resulting polynomial in standard form. Okay, let's do one more example, again to match up that pattern. Let's look at maybe x minus 2, x plus 5. See here I'm starting to mix up the signs of the a and the b. So the a here is negative 2 and the b is positive 5. If we multiply these out, we want the sum of these two numbers to be equal to the coefficient of x. So negative 2 plus 5 is going to be positive 3. And the product of these numbers, negative 2 times 5, that's going to be the q. So negative 2 times 5 is negative 10. Okay? So this is the multiplied version of this factored polynomial. Okay, this is it in standard form. And we can go forwards and backwards by using these patterns in reverse. The process of factoring is the process of getting comfortable with reversing these computations. Here, when we start with the factor form, we can multiply this out using polynomial multiplication, or we can use these conditions to figure out what the coefficients are going to be. When we factor, we reverse this process. So we start from a polynomial that's multiplied out in standard form. We usually use quadratics. And then we'll try and choose an a and a b so that their sum is equal to the coefficient of x and their product is equal to the constant term. Okay? So that's the basic idea. Let's try to do this in reverse, and I'll write out the patterns that we're looking for over here. Completely in terms of these conditions. So what we want to do is we want to take our quadratic and we want to think of two numbers, a and b, which together, when we sum them, give us the coefficient of x, and whose product gives us the constant term. So this is the quadratic that we're going to start with is going to have this type of a pattern, and it's going to be our job to figure out the a and the b that match up perfectly with both of these pieces. Okay? When we find those A and B, we know that this factors out into x plus A, x plus B. Okay? All right, so let's do a few examples. Let's look at x squared plus, let's pick a good one. How about 6x plus 5? Okay? So our job now, when we look at this polynomial, is to try and figure out how to choose A and B to match up the coefficient of x with their sum and match up this, this constant term with their product. When you get comfortable with factoring, you'll go through different possibilities in your head quickly. Okay, so this is a process that really requires practice. You can start with either coefficient. It's really your choice which one you work with first. And what you want to do is list possibilities, list different collections of numbers that can combine to give you that number. So in this case, we might start with this constant term. We might ask, what numbers can I multiply together so that their product is equal to 5? Right? And there are going to be sometimes lots of possibilities, sometimes only a few possibilities, and sometimes there'll be possibilities that you'll discount, you won't worry about. I could multiply square root of 5 and square root of 5 together, and that would give me 5. But that's not really going to factor very nicely, so it's not something that I would expect to factor by hand. So try to work through, integer possibilities. You could combine positives and negatives, you can combine big numbers and small numbers, numbers that are almost the same, and you just want to look through all the possibilities. So I want two numbers who multiply to 5. This doesn't really have that many possibilities because 5 is a prime number. So if I'm only working over the integers or the whole numbers, then I don't really have that many possibilities. There are no factors, no smaller factors that produce to make 5. So it's a reasonable choice to try and come up with a pair of numbers that produce 5 as a product, just because I don't have to worry about different cases, different possibilities. So I can have 5 and 1 are integers that multiply to give me 5. And this is something that you will need to worry about when we consider some more complicated problems, but I could also have negative 1 and negative 5. Those are going to multiply together to give me 5. So those are kind of the two possibilities I have for A and B, and I want to pick the one that matches up with this middle coefficient if I can. If I can't, maybe it doesn't factor nicely. All right, so 5 and 1, or negative 1 and negative 5. Their product is 5. Their sum is positive 6. So 5 plus 1 is 6. So 5 times 1 is 5. 5 plus 1 is 6. 5 and 1 are the choices that we want to make for the A and the B. It doesn't matter which one we choose to be A and which one we choose to be B. We can swap them around, but those two numbers should combine to help us factor this quadratic. Okay? So I can write it as x plus 5, x plus 1. All right? Now, let's consider a little bit more complicated example where we have more possibilities to worry about. What about x squared plus 5x minus 6? Okay. So here we've got another polynomial. Again, we have a p and a q, a coefficient of x and a constant term, and we're trying to find two numbers whose product is this constant term negative 6 and whose sum is this term positive 5. Now, in this situation, one of these terms is negative. I don't want to think about this as a different case. I want to use the same process that I did for the first example, but we do have to worry about that negative sign. That does come into play when we're thinking about these things. So the sign here, the negative 6, that's attached to this constant term. So I am going to need two numbers whose product is equal to negative 6. All right? Now we think about all the possibilities. What are some nice integer numbers that combine to give us negative 6? So 6 has some factors. 6 has 1 as a factor, 6 is a factor. Not very interesting factors, but they still count. But 6 can also be produced by multiplying 2 and 3. Right? 2 times 3 is equal to 6. So we've got some more possibilities here. We want to go through the possibilities and then pick the one that matches with the other term perfectly. Okay, so maybe we'll list them down. So we have to produce a product of negative 6. So I expect that one number is going to be positive and one number is going to be negative. That's the only way I can get a negative product. One negative, one positive. So I have a negative and a positive, and the possible combinations would be 1 and 6 or 2 and 3. Those are my two numbers that are going to combine to give me a product of 6. And then we could have positive, negative, negative, positive, positive, negative, negative, positive. So really there's 4 different choices here, 4 different sets of numbers, right? So I could have, the 1 could be negative and we use a positive 6, or we might have the 6 being negative and the 1 being positive. That's another possibility. And the same kind of thing with the 2 and the 3. The first one could be negative, or the second one could be negative. Either of those would work. So when we're factoring, we kind of work through these things carefully in our heads and try and figure out what combinations are going to give us exactly what we need. The possibilities that we've chosen here, 1, 6, 2, 3, with one of those two numbers being chosen to be negative, they have to combine to give us this middle term. So we have to add these two numbers together to get positive 5. All right? So you might think 2 plus 3 is equal to 5, and you'd be right, but remember that one of the two numbers that we're choosing has to be negative so that their product is going to be negative 6. So because one of these numbers is negative, neither combination of negative 2 times 3 or negative 2 times negative 3 is going to work for us. If I add negative 2 and 3, I get positive 1. If I add 2 and negative 3, I get negative 1. So these don't work. That leaves us with these possibilities to consider. Negative 1 and 6 or 1 and negative 6. So if we add negative 1 and 6, we get positive 5. And if we add 1 and negative 6, we get negative 5. So it turns out that negative 1 and 6 is going to be the choice that we want. That's going to be the thing that factors properly. So once we know that those two numbers satisfy both the constraints that we need to factor this polynomial, we go ahead and factor it. We can write this as x minus 1, x plus 6. Okay? And that's essentially it. When you're factoring, you have these two conditions. I want to find the two numbers whose product adds up to the constant term and whose sum adds up to the coefficient of x here. And I just go through the possibilities until I land on one that satisfies those things perfectly. You have to be aware that this doesn't always work. Okay? So let's look at some other examples. Suppose I had x squared plus 4x plus 5. If I tried to factor this, I would need a product of my numbers to be equal to 5 and the sum of my numbers to be equal to 4. Okay? And here we're going to run into trouble, right? If I try to multiply things up to 5, if I'm just worrying about integer possibilities, 1 and 5, 5 and 1. Everything's positive here, so I expect those both to be positive, but neither of these combinations is really the same combination. This combination doesn't add up to 4, so this doesn't work. It doesn't factor. Okay? Contrast that with 1 x squared plus 4x minus 5. Here, if I think about things whose product is negative 5, I have negative 1 and 5, or 1 and negative 5. And now, there's a combination -1 and 5 that adds up to 4. So this version of the polynomial does factor. Okay? So it's not obvious when you look at a polynomial whether it's going to factor or not. You have to try out the possibilities and make sure that both parts of the polynomial match up. Okay? So this guy would factor into x minus 1, x plus 5. That's really the fundamentals of factoring quadratic polynomials. There are more complicated versions of these problems that factor using more complicated numbers. You could have factors that included fractions or decimals. Those are all fair game. They're all possibilities. But they aren't things that you would usually try to see by hand or just by eye. Okay, so this is the kind of basic idea behind factoring.